Good morning. We were talking about buckling. Means when you have these compressive loads on a structure. What's going on? And if the load gets big enough to a critical value, then you get large deflections, transverse deflections. It doesn't necessarily mean the thing breaks, although if you keep doing it, if I kept doing this to this ruler, it certainly would. Okay. Here's what we had. This would be called a beam because it's horizontal. If it was vertical, it would be called a column. And if the beam has a length L, the critical load to buckling
that's not good.
is pi squared EI over LE squared.
Okay.
LE is the effective length.
You look so plugged, dude. Yeah.
Some of you need to put your stuff on mute.
Huh? Do you feel better today?
Oh yeah. But I still want to sleep in the morning.
On both ways.
LE is equal to L. Not very clear. You have simply supported ends, that's where they're free to rotate. So they can, the effective shape would look like one I've drawn. On the other hand, if you build in the ends, L gets smaller, which means the critical load gets higher. And built in would be no slope here, so the deflected shape would look something like this. Okay. Actually, it turns out that the civil engineers have got some more conservative values for LE. The plus, it's equal to L for simple supports. I think it's about 0.65 L for built in. And you can find these for both editions of Juvenile and Marshak in figure 527. Figure 577 has a table. And these are what you should use in design. They're slightly more conservative. The stress that goes with this we're going to call that sigma C because it goes with this critical load FC. It's FC upon A. And you get buckling.
We also get the material selections.
I'm going to call this SB.
That's true. I mean, honestly, probably just gonna do it in person here.
Huh?
Probably just gonna do it in person.
Somebody needs
Boss,
to
hey,
order.
boss, mute yourself real quick.
You need to turn your,
Nils, shut up.
Like not flash.
No, just like we're just,
what's going on?
so
Yo, Nils.
Sorry?
Sorry, I was calling him.
how do we calculate the cutoff?
Dr. Wag.
Okay, then put it back. Put it back.
Yeah.
Okay, clear out. All right, I'm going to call this SB, like a strength for buckling. The book calls it SC, but SB then, we rewrite this and we write I as A times rho squared, then you get the following. The rho is called the radius of gyration. So this ratio is the ratio of the actual length to its transverse length in terms of radius of gyration. So this is a slenderness ratio. This has the units of stress, and so this has the units of strength. For a circle, then rho is d upon 4. If you have a rectangle, it's always, let's call this H, okay? It's always going to buckle, and this is the smallest direction, it's going to buckle in this direction, okay? It's not going to buckle this way. And so then to get rho, this is A rho squared, so I divided by A, which is BH. B is the breadth. I would be 1/12 BH cubed. So it's just going to be H. And the square root of 1/12 with 289. So when you're dealing with a rectangle, and you're getting these, the stress, the strength, this H is always the smallest dimension. Well, we started talking about this last time. Are there any questions on that?
Is
Is it kind of a
SB
trade-off?
just the buckling strength?
This is a buckling strength. Strengths are limiting values of stresses. Another one is the yield strength. Okay. And I'm going to use consistently uppercase S for strengths. So if this is sigma C, plotted versus the slenderness ratio, then this curve here looks like 1 upon the slenderness ratio squared, so it looks like this. On the other hand, if you put this in compression, there would be a yield strength. Okay. And so at the outset, you would think the compressive component would be okay if it was below this line. In fact, it doesn't get quite up to here. And so what we're going to do is we're going to fit this with a parabola up to some point. Let's call it L bar, dimensionless. It's this ratio, but this is the value of it. It's not that clear. And after that, we'll have this SB. So this is a little bit less. We'll call this SY minus. when the slenderness ratio goes to 0, it is SY, but it comes down from that. The foot we're going to use here is from Johnson. This bending, this buckling strength comes from Euler. Euler solved this problem a few centuries ago. So this is what we're going to do. When the slenderness ratio is less than L bar, we'll regard that as squat, and the strength will be SY minus. When it gets above LC, we're going to regard that as slender. In which case, for a safe design, we're going to want sigma C less than SB. And to get this, we'll do what Johnson did. He took an equal to SY minus this parabola, which will have a coefficient, which is a stress. We don't know what that coefficient is yet. Times the slenderness ratio squared. And the way Johnson did this is at L bar, he had this SY minus match SB. And he also matched the slope.
Is that 1 over L bar?
Sorry, 1 over L bar? No, this is at L bar, if you like. This line means at LE upon rho equal to L bar. Okay? I perhaps should have written LE upon rho equal to L bar. So what this line means at L bar, that slope is going to be the same as the slope of SB. This is again at L bar. Well, maybe if I write this out a little more detail, you'll see how it works. This first thing here, let me do this, SB. That's what SB is. This was LE upon rho. LE upon rho is equal to L bar, so it's L bar squared. And that's going to be equal to SY minus whatever the sigma is times L bar squared. And then we can differentiate. We differentiate the 2 down here, so it'll be a minus 2 on the top. And this would be L bar cubed. If we differentiate this side, again, we get a 2. Okay. So hopefully that's clear. What this equation is matching the values here at this point. What this equation is matching the slope. Now we have to solve these. Okay. So we're going to solve for them. Well, 2, I've got a sigma L bar squared up here. So 2 can give me that. I get rid of the 2's and the minus sign. Then what 2 has is that pi squared E over L bar squared. I took one of these L bar and put it up here. It's sigma L bar squared. Okay. Then I can substitute in here, and I'll get pi squared E upon L bar squared is sigma L squared. I have another one there. So this gives me that sigma I substitute that result, let's call this 3, say. So I can substitute sigma times L bar squared of SY upon 2 sigma L bar squared is SY upon 2. And this gives me what L bar is. L bar squared multiplied by 2 multiplied by L bar squared, put it across this time. That's what L bar is. Dimensionless number. This is dimensionless. Then I can substitute back for sigma back here. Divide by 2 by L bar squared. So sigma equals SY squared upon 4 pi squared E. Let me summarize that, what we've got. So here's a basic thing we're going to have. We'll have SY minus it's SY minus sigma divided by LE upon, sorry, times LE upon rho. And this is going to be true less than equal to L bar as if, on the other hand, when the slenderness ratio gets bigger than this, we're going to have so this is what we're going to use in design. So let me do an example. But these are the key. This example is a connecting rod. Connecting rods get loaded in compression.
Wait, Dr. Sinclair, could you move
Yep.
that paper down a little bit?
Is that okay? Yep. So here's a connecting rod. This is from an 8 horsepower Briggs and Stratton engine. And when this is top dead center, like that, Okay, when stop dead center and aspiring, then this thing's loaded in compression. Of course, the piston moves down, okay, and this thing goes off to the side as it goes. It's on the crankshaft, but when the crankshaft is right here, right underneath it, it's loaded in compression. It's also loaded in compression on the upstroke, but it doesn't have as big a force. So connecting rods get loaded in compression. Okay. Now they have a simple example in the book. We'll do that, and it'll show you how these things work when you find a new design. What you're going to have to do here is you have to obey both of these rules, but you're not quite sure which one you're in when you're doing design. You're picking the diameter, say, or picking some part of the cross section, and so, as is often the case in design, you have to make what you might call an estimate of where you're going to be and use the appropriate formula. Then you have to check that you actually are correct. Let me do this then. This is I'll give you the specifics, but this is a sample problem 511. And their connecting rod looks like this. Actually, both the ends and the figure are identical. My drawing, they're not, but it has a cylindrical cross section. I give you the following specifics. It's a long connecting rod. It's steel. And it has a yield strength. This would be a tool steel, high strength steel. And I want a safety factor of 2.5. Typical safety factors with buckling are more than 2, okay? Maybe 3 on occasion. Then what we're going to design is design the diameter. When we start to do this, depending on what diameter we have, that's going to change what rho is. It's going to change the value. We've got LE. LE is equal to L because it's simply supported. But we're picking this rho, so we don't really quite know which of these ranges we're in. So at the outset of doing this design, we have to make an assumption. Well, let's assume that it's slender and try this. But once we're finished doing this, we'll check and see if this is true, okay, that this analysis holds because our slenderness ratio is bigger than this L bar. And in that case, we've made the right assumption. If it's not, then we have to go back and redo this. And this happens quite often in design. You have to make or a guess or an estimate. What happens is in practice, when you design a bunch of these things, you tend to know. You're fairly often guess the right thing at the outset. But we're going to assume it's slender. So what we've done is we've assumed that whatever D we get, the slenderness ratio is going to be bigger than L bar. We'll have to check. Later to make sure this is true. So if it's slender, the thing we see is F upon A, and that's going to be SB upon N. Where N is the safety factor. Okay? And SB was here. It's this pi squared. LE is equal to L. Well, we know that A is pi d squared upon 4, and rho is d upon 4. So if I substitute in here and multiply across by A, I put A up here. I substitute rho is d upon 4. So it's going to be d squared upon 16. Well, this is an equation for d. Here's a d squared, and d squared is d to the 4th. I multiply all these across and times f. 4 times 16 is 64. N L squared f. Then I divide by this pi qb. So I take the 4th root. N was 2.5. L was 1 meter. This I need to put in newtons, so I'll multiply by 10 to the 3. This is in gigapascals, so it's 203. If I put it in pascals, so I have all my units in newtons, meters. Then that's the case, I have to multiply by 10 to the 9th. If we calculate this, this gives me D. I'm at 0.037 meters or 37 millimeters. That's right, 37.8 millimeters. And this is a possible solution. Now we have to check and see what the slenderness ratio is and see if our assumption at the outset from doing this problem was correct. So let's calculate LE upon rho. Well, in millimeters, this would be 1,000. And rho is D, in millimeters, D upon 4. Let's see, what does that come to? Looks like about 100. $106. What's L bar? L bar is just pi times 2E upon SY. E was 203 gigapascals. SY was 689 megapascals. You could do this in megapascals and just have a 10 to the 3 on top here. That's what I started to do actually, but because the units will cancel. But anyway, I've done it all in pascals. So it's going to be 2,000 times 203 divided by 689. That's about 590. The square root of that is 24. This is 76. So we're okay. So the assumption at the outset was correct, and this is our design diameter. What would happen if the assumption wasn't correct? Well, then we'd have to go and solve so this worked out, but if it was not, then you've got to use the Johnson formula divided by n. And its times. This is simply supported, so LE is L. I might probably put this n across and put an A. I'll get the following. Rho is D upon 4. If I multiply through by D squared, then this will be the only term with D squared, and I can solve. And so you'll get D. It'll be D squared, so it'll be a square root. So you would substitute in this and go get D, and now it would have to work. This is an either or situation. Either you are slender or you are squat. There's no third case, and so this would have to work. Okay. Any questions on that? Well, some of your homework needs you to do this. Okay, when you do the homework, this is a very simple problem. There's a second sample problem you can see in the book right after this. Okay. In this case, LE was equal to L. LE will not always equal to L, and you really should go get the more conservative, larger values of LE, which have lower buckling strengths. You should get the larger values from that table, which is that figure number that I gave you. And you will have to, when you start doing, make a guess whether it's slender or squat. And sometimes you'll be right, sometimes not. You just have to redo it. Okay? But this approach would work for either. Okay? More or less, this formula works for either. For squat, and the other previous formula will work for. Are there any questions on that? Let me wrap up buckling with a few other comments here. there's quite a bit more to buckling. Quite often your loads are not lined up right through the center line. Let me show what I mean by eccentric loading. There's the center line. And the loads could be off some small amount from the center line. So that's eccentricity. Okay. Well, that reduces a moment about the center line, and that increases the chance you buckle. It's not going to be examinable because we haven't done homework problem on it. But if you encounter this, you can start off by looking at Juvenile and Marshall, section 5.13. Same numbered section in both editions. Okay. And this occurs sufficiently often that there's some standard approaches for dealing with it. Okay. And what it's going to do is going to tend to lower the buckling strengths. When you have eccentric loading, you always promote buckling. When you have imperfections, you can promote buckling. Well, imperfection is anything from a perfectly straight beam or column. And sometimes, so if you had something like this, that would promote buckling. On the other hand, if you had something like this, and you ignored this extra part here, that would not. If anything, it would perhaps slightly inhibit buckling. So this was the case with the ruler, my long ruler, is it wasn't dead straight. And so that dropped the buckling load by a factor of 2. You don't want to think that that's too likely. That's an extremely slender column or beam, that ruler, and seldom are you applying compressive loads to a structure like that. Occasionally, what you need to do with buckling is you need to get the deflection. Whenever we did this buckling, I suppose it was simply supported. If you look back at the little analysis, which was like the analysis that Euler did, then we got the shape. We said the shape looks like this. Sorry. but we didn't know what that was. Okay? And you can't determine that with the theory we're dealing with. You can find the load which promotes it. Okay, if you hit that load, that it'll go into that shape. And with this thing here, depends upon how much the load exceeds that critical, and it grows with it. And you need nonlinear. Sometimes you need to know this because you may be deliberately buckling something to make contact with something, like a switch. Or you may accept a certain level of buckling and you just want to make sure you still have clearance and it doesn't hit, something like that. Okay? So sometimes you need to know it. Well, the way you need to actually need nonlinear beam theory. Which gets the deflections. And it's not simple. There is an excellent book. It's out of print, but I imagine you can still get it online. It's 1962. So this is something you'd have to get from Amazon or something like that. There may well be some other books, but I've used this book for a number of years, and it's an outstanding book. Strangely enough, Fish Fay is Australian. New Zealanders suspect that Australians are not literate, but nonetheless, this guy wrote a great book. Okay. It's unlikely you'll end up doing this. You can do this with finite element. It is tricky to do with finite element. So if you, in your job, you start to need these actual beam deflections, you're going to have to learn nonlinear beam theory. Okay, it's dangerous to use finite element without understanding this theory. And this is, to the best of my knowledge, the best book for doing this. But it's not often you need this. You're more doing the design thing I did in the exercise. This is not going to be examinable at all. Well, at this point, we're about to switch topics. Is there any questions on buckling?
So the eccentric loading will not be on our
No, it won't be. You won't be examined. It's in the book.
Okay.
And it's quite common. So I gave you a reference, but it will not be examinable because we haven't got any homework on it. Okay. We didn't cover it in class.
The exam is still on the same date. It hasn't moved.
Sorry?
The exam is still on the same date.
Yes.
Okay.
Okay. Well, I put contact, these chapter numbers followed the order in Juvenile Marshall. I thought it was more logical to make this part of stress analysis that we did that. So we've done this deflections. Now we're going to start talking about when do things break. We'll start off today talking about failure theories under single loading. And that leads into fatigue, which is the key thing. Okay. This is our fourth topic. The book calls this chapter failure theories, and that's true. You have a hypothesis of what breaks things, and then you check it with experiments, and so it always remains a theory. The experiments are pretty good here. I think it perhaps more reassuring just to call them failure criteria. This is what we're going to use. Anyway, the respective chapter in the book is chapter 6. Why do we need? Well, we need to understand the loads that produce failure so we can design against them. there's two sorts of designs you do in practice. There's an initial design. We've got a new product or something like that. You certainly want to do this. What often happens in practice is you have a failure. And so then you go back and you try to understand what caused it, and you'll need these failure criteria to do it. Then you can redesign so it doesn't fail. That's very common. As far as we're concerned in this section, in terms of what, I'm going to be discussing today brittle fracture, and yielding. Different materials do different things, and different stresses influence these things. The brittle fracture brittle fractures, this just happened this weekend. I put I was trying to mount a plate on the wall for my wife, and I didn't mount it properly. I didn't have the hook on it. It stayed there for a wee while, and then it fell off, and then it broke. Well, when it breaks, it breaks into pieces. So, the speed with which this happens is very fast. When it starts to break, the cracks propagate at about the speed of sound, which is more than 10,000 feet per second in most solids. So it's over instantaneously once it starts to break. If you go and get the plate or something like that you dropped and put it back together, in this case, it would have been difficult, but sometimes it just breaks into about 2 or 3 pieces. You don't get any permanent set, it fits back together. And it's nearly always bad. There are a number of materials we use in engineering that are brittle. Glass, ceramics, insulation, bricks, wood, somewhat brittle. It's not completely brittle. Cast iron can be brittle. One of the things people discovered is that if you get certain steels or certain carbon content at too low a temperature, they become brittle. And for demonstration of a brittle material, this is not a construction material, just a brittle material. Chalk. So if I break this, then this will fit back together. Well, there's a little third piece there. It fits back together almost perfectly. Okay. There's a little piece that came off the top here, which just fell to the floor. But otherwise, and so I lost that bit, but it fits together perfectly. There's no permanent set. Okay. Yielding, on the other hand, there's other materials. In this case, you do get a permanent set. It may or may not actually rupture. You have to keep loading it after it's healed to rupture. It's not usually as rapid. And it may not be bad in itself. However, when you start to yield things and you have cyclic loading, it's usually the harbinger of fatigue. So it's not necessarily a bad thing, but we're going to try and avoid it because of this. When it just yield, the amount of permanent set is small, displacements are small, and they're not like buckling displacements typically. And so it can be okay as a single time event. Repeatedly, it's not going to be good. So we need to guard against it. Here are some materials. Or steels. Aluminum alloys. Metals generally. Let's see. Here's a paper clip. I'm just going to bend it. It'll bend a certain distance and it go back elastically. If I bend it too far, then I have a permanent set. Okay. If I kept on doing this, that's even bigger permanent set. And then I finally got rupture. So you don't necessarily get rupture when you just start to initially yield, although the paper clip will function less effectively once it has a little bit of permanent set. So now it doesn't clip things together as well. But I can push it back together again. All right, let's take a break for 5 minutes. The stuff you've all seen, I believe, in your courses prior to this, but we're going to apply them in machine design here. So What's the option?
He emailed me to set the mute option for all so that they said some of them they get interruption past 30 minutes because some of the students the mic on they have problem with hearing.
Oh,
So,
so what we do?
so he suggested to do the setting so that everybody get muted. But I'm worried if I set mute option for everyone, then when they will ask question,
Yeah,
they need to ask you to unmute. But you don't follow the
yeah.
everyone. Yeah, that's the problem.
Oh, well, I'll talk about that.
That wouldn't affect anyone's ability to ask a question. They would just have to intentionally unmute themselves to ask a question, which
Okay.
we're all
Okay,
accustomed to.
Okay.
all right,
Then we'll do that.
we'll do that.
I think just the only thing would be before y'all start talking to make sure that y'all unmute yourself. But
Okay.
Okay. Okay. We'll do that. Okay, well, following a request, Baham has muted you all, so when you want to ask a question, you have to unmute yourself. Okay, and I'm not the greatest at picking up these little box questions that come here
Chat box.
in the chat box. So I'm not trying to ignore you, I'm just not used to picking those up, and I don't pick them up. Let me make, before we get back to these failure theories, let me make a comment about this connecting rod. Okay, this is a real connecting rod, of course, and so if it was to buckle in this plane, then this would be like simply supported. Okay, if it's to buckle this way, out of, let's see, how can I show that? This, if it was to buckle this way, then this thing sits on a crankshaft, and this is on a cylindrical pin through the piston, and so in that direction, it's very close to built in. Okay, and I did some measurements on this here, and what you find is that they've got this I-beam, well, I column in this thing here because you get a big second moment of the area. Okay? And they've chosen the second moment of the area so that if you divide it by LE squared, you get the same. Okay, and so the second moment of the area, when it's simply supported like this, is about 2 times the second moment of the area in here, because if you look up the LE for built-in, it's about 0.65, not 0.5. And you square that, you divide it, you get the same thing. So what's happening here is they've made the buckling node. I thought this would be the case. They've made the buckling node this way the same as this way. Okay, and that's one of the things you do, and you can use an I configuration to do that. But you've actually got enough to design something like this. Well, getting back to these failures, let's start talking about brittle fracture criteria. typically in brittle fracture, the maximum normal stress equals the tensile strength. So if I do, there's another piece of chalk. I'm gonna put this chalk in bending. So I'm gonna push up here with my two thumbs, push down here with two fingers. Then if I look at the top of there, the top of this thing here is in bending. I could try just pulling this, but I can't get enough tension on it to break it there. Bending is a lot easier. There's a lesson here. Bending stresses what breaks things in Mech E. So this is good 4-point bending here. It broke close here. It's almost dead straight across. And this is where the Mach sigma B equal to SU happened right here. It can happen anywhere between my two fingers. The bending moment, the bending moment is constant through here. So it could happen anywhere. It possibly happens right where my fingers, maybe my nail hits it or something like that. I don't know. But so it's tension on this side. And again, it broke near this grip here. But if I do it in torsion, I showed you this earlier. This shows you that it's the normal stress, not the shear stress, that's breaking this thing. The shear stress is when I bend it. We're off at 45 degrees on this line here, and nothing happened there. Okay, so if you've got the maximum shear here, when you've got this situation, then the maximum shear occurs at 45 degrees. So you could say it's less. It's sigma B upon 2. There's an average normal stress on this. Okay. If I put something in torsion, though, now the maximum shear stress, if I look at an element on the top of this, and that's maximum. What is the shear equal to? The shear here would be that would be the maximum on the outside. If the shear distribution is 0 at the center, I guess it's the maximum value out here. So that's what the shear is. Okay. Then, well, this situation here produces a normal stress in this direction. These two produce a normal stress. And a compressive stress in this direction. So the normal stress is, this is 45 degrees. If you just have this pure torsion, sigma 1 and sigma 2 are equal to sigma average, which is 0, plus or minus tau max, and tau max is just tau t. So what you have here is sigma 1 equals tau t, whereas sigma 2 equals minus tau t. So if I do this for a piece of torque, since the maximum normal stress occurs at 45, this thing should break at 45 degrees. Well, pretty close, okay? So there's the 45 degrees, that's where the maximum normal stress is. Okay? But and there is no shear stress on that. So this shows you that brittle fracture is governed by normal stresses, not shear stresses. The opposite is true when we start dealing with ductile. There are several names for these theories. The first one we'll deal with is Rankine. And more is what I just said earlier. This is going to be the ultimate tensile strength. I should really put the word tensile in there. So when you load something up in uniaxial tension and it's brittle, the stress strain curve looks like this. It's basically linear elastic, then it breaks. For really brittle material, there's usually a little bit of micro cracking and a little bit of increase in delta. So there's a little bit of wobble at the end. If you actually do this. But when it first starts to micro crack, to be conservative, you call that the ultimate strength. It might get to something slightly higher than that. Okay. Well, we can do this more generally in 2D, the Rankine approach. So I'll have two principal stresses. And what we just said is when sigma 1 equals SU, this thing broke. If this is 45 degrees, then above this line, sigma 1 would be less than sigma 2. So then sigma 2 is going to dominate. So below this line, sigma 1 is bigger than sigma 2. On this line, sigma 1 equals sigma 2. Above this line, sigma 2 is bigger than sigma 1. So it sets the limiting value. And what Rankine did, he said the same thing happens in compression. Okay. So he said, let's talk about magnitudes here. On this part here, the magnitude of sigma 1, okay, this distance out here, sorry, on this part here, the magnitude of sigma 1 is bigger than sigma 2. Ignore the minus signs for a moment. On this line, they're equal. Over here, sigma 1 is bigger, so it sets the limit. Sigma 2 is bigger, so it sets the limit. And then Rankine just drew this in like this. And oftentimes, so SUC here is the ultimate strength and compression. You're pushing the thing together and it breaks. It's a little bit hard to see how this happens, but it's like the stress concentrations. The material you've got, okay, and I'm not talking about buckling or anything like that now. If you've got a slab of this material, a slab of this stuff here, thin, and you push it, there are little wee voids and other imperfections inside this. And one of the things that happened when we did tension around the hole, we got a bigger tension on the sides of the hole, but we got compressive stress directly in front of the load. Well, the same thing happens in reverse when you put it to compression. You actually do produce some tensile stresses, but nonetheless, and they're comparable. Nonetheless, it's a bit harder for connecting up. So typically, SUC is greater than SU. Okay. Oftentimes we don't have it. So when we don't have it, we just assume it's equal. And that's a conservative approach, in which case this Rankine approach is quite good. Okay. So if you assume
Dr.
this,
Sinclair,
this approach is quite good. Yep.
do you mind writing a little bit bigger?
Oh, sure.
Thank you.
Sure. Every so often I revert to my normal writing line. I realize I'm supposed to write bigger. My mistake.
It's all good.
Okay. So there's a more theory. And this is when you've got an SUC and it is bigger than SU. If you run an example, concrete. SUC, these are strength, so these are magnitudes, is about 4 times SU. And you see this in life. How does concrete fail? Well, most of the time it doesn't fail in compression. But what happens is that some of the, perhaps it's on a driveway and some of the material underneath the concrete moved or gone away. Okay, then it goes into bending, and then you get a crack and it starts to break. So what the Moore theory does is the following. So when we make this assumption, these things are really further out and we're ignoring that. So this is not bad. Okay. And if SU is just a little bit bigger than SU, this is not bad. But when you have a significant difference, and frankly, we haven't measured a lot of these things, so I don't know. The same criteria in the all tension, okay, namely the biggest principal stress equal to SU means failure. The same criterion in the all compression. But what Moore does is he doesn't let you get up into these corners here. Okay. There's not a lot of data on this. To this extent, there is some data. It tends to be above this line, but not all the way, perhaps up to the quarter, up here. So this is conservative. And so in practice, if you don't know what SUC is, you assume they're equal, you can use Rankine, that's fine. If somebody gives you SUC and it's bigger than SU, it's not going to make much difference if it's just a little bit bigger. But then once it starts to be 1.5 times or bigger, then this is probably a better, more conservative approach. Well, you find maximum normal stresses are what break things. When plates break, they they break at 90 degrees to the edge, typically because they break in bending, just like I showed you with the chalk. And so that works. Yielding, on the other hand, is driven by shear. As you're probably told, materials, metals have dislocations, and dislocations can move sideways and they create slip. If they move too far, then when you take the load off, they don't come back. Okay? The simplest possible approach, and still a very effective approach, is due to Tresca, although some people credit this to Coulomb. So we'll put a piece of metal under tension. And if this, oh, it's a prismatic bar, just a fixed idea is we can make it cylindrical. And this will extend under this action a small amount. Within the elastic region of most metals, you probably can't see it. Okay. So sigma here, the uniaxial stress, is F upon A, and the strain is delta upon L. In this uniaxial tensile test now, we'll have some quite large deflections eventually when things start to yield. There's an initial elastic regime. Which has a slope of Young's modulus. And then you start, sometimes it's Balchinger effect and other things here, but to simplify things, you have a far less stiffness once you get to yield. Orders of magnitude less. At least 2 orders of magnitude less. It won't necessarily be as clean as this. As I said, the Balchinger effect is a bit of an overshoot, and with aluminums, so there are different curves here. Aluminum's bend like this, steel does something like this, and so on. But this does to characterize it. So you get yielding. Well, sigma x, the stress state, is equal to Sy. Sigma y, there's no stress in the lateral direction and no shear stress. Carmax in 2D, we had this earlier, the sigma x minus sigma y upon 2 squared plus tau xy squared. And these two are 0, so it's just sigma x upon 2, which is sy upon 2 at yield. So here's a summary of Tresca then. In general, that was uniaxial. How do you get tau max? It's the maximum of the half the differences of the principal stresses. And you're going to get yield. And this is really the basic physics of yielding. It's driven by shear. It's unfortunate that we record these uniaxial stresses, we call this normal stress at yield. That's not what's causing it. It's shear stress. We're going to have a more general von Mises criterion, there'll still be shear. So it's one of these misnomers. When people did these tests very early on, they called this the yield strength, which it's a term we still use, but the implication is it's normal stress causing it. Well, in this particular application, it does consistently yield in a certain normal stress. But the underlying physics is shearing. Okay. It's very important to recognize that. That's why this is really a good criteria to remember even today. Von Mises has supplanted it in practice. We'll deal with von Mises, but it gives you the simplest version of the underlying physics, and it's right. Okay. So let me do some more general cases. So let me go 2D, and we'll have sigma 3 equal to naught. First one, so they're both positive. Then I'm going to look at the maximum of these differences. These are both positive, okay? So this is going to be smaller than this. This is 0 from sigma 1. Okay? And this will be smaller because it'll be 0 from sigma 2, but sigma 2 is less. So this is the one that holds. And so I just get 1/2 sigma 1 equals sy upon 2. So sigma 1 equals sy. Okay. So I would have had 1/2 sigma 3 minus sigma 1 equals 1/2 sy, and the halves cancel. And the sigma 3 is 0. Likewise, if sigma 1 is greater than naught and sigma 2 is greater than naught, but now sigma 2 is greater than sigma 1, and sigma 3 is still 0. And if I go through this shopping list, the biggest difference I'll get will be sigma 2 minus 0. Sigma 1 minus sigma 2 would be smaller because sigma 1 is not 0. And sigma 1 minus sigma 3, this is 0. This is sigma 1 upon 2, where sigma 1 is less than sigma 2. So this just gets me. So let me start to plot where things are going to be okay in 2D. Tresca. This first case is 45 degrees. Sigma 1 is bigger than sigma 2, and then we get yielding when sigma 1 is SY. Sigma 2 is bigger than sigma 1 over here, we get yielding, and this is equal to SY. I'll come back to this. What about in compression? Well, the yield strength doesn't change in compression as long as you don't buckle things, in which case you've got different stresses. But then again, if I go through the shopping list for Tresca, the biggest difference I'm going to get is the magnitude of sigma 1 minus 0, because the magnitude of sigma 1 minus sigma 2 is going to be less and sigma 2 is less. So this is just going to give me. And likewise, if I reverse this, but now the magnitude of sigma 2 is bigger, then I'm going to get sigma 2 is minus SY. So on this little figure, over here, sigma 1 is bigger than sigma 2, in which case it's the limiting value. And here, sigma 2 in magnitude is bigger than sigma 1, so the second one holds. What about in this region here? So sigma 1 greater than naught, sigma 2 less than naught, okay? And sigma 3 is equal to 0. Then tau max, well, sigma 1 minus sigma 2 will be the biggest value, okay? Sigma 1 minus 0 will not be as big, and sigma 2 minus 0 will not be, because these, so, because this is negative and this is positive, then when I take sigma 1 minus sigma 2, I get sigma 1 plus the magnitude of sigma 2. So what I have here, that I have sigma 2 equals sigma 1 minus SY. That's just a straight line. When sigma 1 is 0, it's SY. When sigma 1 is SY, it's up here. It's just a straight line like this. So this is just like Moore. Okay, only it's for different physics, it's for yielding. So the inside here, no yielding. You get yielding when you get to the boundary. So that's what the Tresca condition looks like in 2D. Let me do one other special case. A couple of others. Hydrostatic compression means all the principal stresses are equal. And then tau max is the biggest difference of these principal stresses. Well, there are no differences. They're all equal. So tau max equals 0. So it never yields. So if you, or butter is something that you yield on a daily basis, to spread it on your toast or something like that. Well, if you took some butter and put it 20,000 leagues under the sea, it would not yield. A little wee bit of pressure of your knife on one side and compression, then it'll yield. But, so hydrostatic compression never yields things. Okay? And there have been some tests like this that show that this is the case. A common situation is for shafts under bending. Then tau max is sigma 1 minus sigma 2, or sigma x minus sigma y upon 2. If one of them is bending, it'll be sigma b. And then tau xy will be tau t, because the shaft is committing some torque, transmitting some torque. This is basically just 1/2 sigma 1 minus sigma 2. Okay. When you have in 2D, you have sigma 3 equals 0, sigma 1 and sigma 2, a sigma average plus or minus tau max. So this is exactly from the shopping list we had. So we're going to put this equal to S y upon 2 r squared to get rid of the square root sign. If I multiply 3 by 4, then I get the following. There'd be a 4 there, so that gets rid of that. But I get a 4 here. And I multiply by 4, I get rid of that too. So what this tells you is what dominates yielding of shafts tends to be the shear that's been transmitted due to the torque. Okay, that's what dominates. It dominates more than the bending. There's an alternative criterion which is used more often, although in practice when I've been consulting, I've used Tresca numerous times, it's easier. But there's arguably a somewhat better approach. It agrees with the data slightly better, due to von Mises. What von Mises did, he developed an equivalent shear stress. We'll put a subscript E for this equivalent stress. Here's the definition. And what this looks like is a root mean square of all the shear stresses. So it's what Tresca did is he used to pick the maximum of each of these. They take the square root and it's a different coefficient, but he picked the maximum of these differences. What von Mises said, if you have some other shear and other planes, that they may influence this stress. So this is like, you could regard this as physically as the root mean square shear. The book has some energy terms for this, and there is an energy interpretation. Physically, what's happening is shear stress is still causing the yielding. So let's look at uniaxial tension. Uniaxial tension at the point of yield will have sigma 1 equals Sy and no stresses, other principal stresses now, uniaxial stress. Then what would sigma E be? Well, this will just be Sy squared. This will be 0, but this will also be Sy squared. So I've got two of them divided by a half. That could be 1. I take the square root, so sigma E. So that's the von Mises criterion. Let me summarize it. That is, we have sigma E. Whoop, my mistake. Well, we can go through and look at a bunch of special cases with this. Okay. Let's suppose sigma 3 equals 0. So it's 2D problems. Then what we'd have at yield is we'll have sigma E sigma 1 minus sigma 2 squared. This will just be sigma 2 squared. And this will be sigma 1 squared. So here I'm going to have a sigma 1 squared plus a sigma 1 squared, two of them. Here I'm going to have a sigma 2 squared plus a sigma 2, two of them. The 2's cancel. And here I'll have minus sigma 1 minus sigma 2. And it'll be a 2, and the 2 will cancel. So what I'm going to get So at yield, according to this criterion, and in sigma 1, sigma 2 space, this is just the equation of an ellipse. You can see if sigma 2 equals 0, that sigma 1 equals sy, and we already did that. The same thing is going to happen if sigma 1 is 0, sigma 2 is going to be sy. We could have them equal to plus or minus sy. So it goes through these 4 points. If sigma 1 equals sigma 2, you'd have, let's call them sigma 2 equal to sigma 1. So sigma 1 squared plus sigma 1 squared minus sigma 1 squared. So again, you're going to get plus or minus. So if I drew straight lines here, this would be Tresca. Von Mises is an ellipse. And you could go through and put, say, here, let's call this sigma 1. Here, there's sigma 2. You could put, say, for a line here, sigma 2 equals a half sigma 1. When you did that, you get a half. Let's see. If I put that in, I'll get sigma 1 squared plus sigma 1 squared upon 4 minus sigma 1 squared upon 2. That's 1 plus a quarter minus a half is 3/4. So 3/4 equals sy squared, then sigma 1 equals the square root of 4 upon 3. So as I indicated here, this is bigger. This goes outside. You get values slightly bigger. If you go through here, instead of getting a half, which would be Tresca, you get something slightly bigger there too. And the reason why this is often adopted is it tends to agree with the data better. Let's see. I thought I had a little sheet there. I'm not quite sure where I got this from at this point, but let me show you. So the dashed lines here are Tresca. I've forgotten what I wrote here. Here's something that's a bit close to Tresca, okay? And but by and large, the data tends to agree with von Mises slightly better. Now, here, von Mises is not conservative. Well, that's okay. We're going to have a safety factor anyway. Okay? And so generally, so it's the preferred criterion today. In finite element codes, I'm pretty sure it's the only one you're going to get. Okay? On the other hand, in terms of quickly thinking about things, just the Maxwell shear works pretty darn well. And it is conservative. So you won't be making errors here. Let me give one last special case here. I didn't find a fit, or maybe I didn't look carefully enough. I didn't find a figure in the book for that. But let me do hydrostatic compression. Just to emphasize this, again, this is the state sigma 1 equals sigma 2 equals sigma 3 minus p. So all these differences will be 0. So sigma e equals 0. So it never yields. So you will not yield things when you put them under all-round compression. Actually, you wouldn't yield them if you put them under all-round tension. It's just kind of difficult to do that. How would you apply the tension? It's difficult. So, but compression you can. Okay. Right. You should be in position to do all of problem set 5 now, and we'll discuss that a little bit on Wednesday, and then we'll move on and talk more about other failure theories. Do you have any questions you'd like to answer?
Yes, sir. Could you put that second to last paper back up with the
This here. That one?
the one before it where you were writing out the equations? I missed the last equation
Oh,
for the ellipse.
this one here?
Yes, sir.
Sorry, I should have taken it away so fast. If you're used to the equation looking like y squared upon b squared plus x squared upon a squared equals 1. Now this is just a different form of the equation of an ellipse, actually. But and so I was just doing this point here and showing you that you do get sigma 1 bigger than the yield strength with von Wieser. That doesn't happen with Tresca. Tresca is everywhere inside this well, it's not really these are not equal sides. Okay, so it's a 6-sided polygon, but they're not equal. But it's circumscribed by von Mises. Okay, and so this goes out, and you get a little more. I think this is about 0.55 or something like that out here. Whereas if you had Tresca, it'd only be 0.5. Any other questions? And
Dr. Sinclair, I just have a personal question when everyone else leaves.
sorry?
I just have an individual question when everyone else leaves.
Okay. All right.
I have a question about test.
Okay. And this just the best data that I could find from this here. And it shows you that the von Mises works slightly better. Okay. But Tresca is not too bad. Okay, doke. Well, that's it.
There's one more question. Gabe Gabe was quiet when he asked.
I have a question about the topics on test 2.
What's the question?
He has questions about test 2.
Oh, well, just 2. Okay, well, why don't we start the class on Wednesday? I'll open it up for questions about test 2, okay? Because some people have left by now. So I answer questions about the test when everybody is pretty much there. So at the beginning, I'll tell you what, in the break, remind me, when we take the break in the middle of the class on Wednesday, if you've got questions about test 2, then you go ahead and ask, okay? That way everybody can hear the answer, or everybody's in class can anyway. Okay? Anything else?
I have a random question.
Okay, a random question, go ahead.
Do you like Vegemite?
No, I'm Marmite guy. Vegemite's what Australians eat. Marmite's what New Zealanders eat.
Are they like the same thing?
Vegemite's a vegetable extract, and Marmite's a meat extract.
Ah.
They're not quite the same. They have a very similar flavor. My wife can't stand either one of them. Okay.
Vegemite is horrible. I hate it.
Well, the thing is, you got to be very careful you don't put too much on. Okay, just a very small amount is okay. But yeah, no, I'm fine with Vegemite. I went to high school in Australia for a while and got used to Vegemite. But no, and Marmite the same way. You just want to put a small amount on, and then I find it quite tasty. But some people never like it. My wife tried it several times. She's from Texas, and she thinks it's horrible. So it's a matter of opinion. But
Maybe I'll have to try it with a lower quantity.
very small, yes. Piece of toast, a bit of butter, and then a very small amount, and see if you like it. Okay, yeah, that's key.
Gotcha. I'll give you an update on that.
Okay. All right. Any other questions? Okay, well, have a good day.
Dr. Sinclair,
Yeah.
I had emailed you and briefly talked to you about a month ago. For this next test coming up, I have mandatory military training in Mississippi, and I won't be here for it.
Yes, I got your email.
So,
Yes, okay,
yes, how do you want to go about just rescheduling this?
okay, yes, all right. No, let me tell you what we'll do. Since you've got two tests and a final, we would just scale up your score in the first test and the final. Okay, so
Okay,
that's what we'll do. That's what I did to people who missed the first test. Now, if you start to miss two, then we're going to have to give you a makeup. Okay, so we
no, I shouldn't be missing the final for any reason.
right.
So,
And the final will have some of this stuff examined, and the last stuff in the course builds on this anyway. And so you'll be getting examined on this stuff. And so this is Matt Callow, is it? Who am I talking to?
Nick Cabot.
Okay, okay. Let me write. Can you spell your surname, please?
Yes, it is K-A-B as in boy, A-T-T as in tree.
Okay, all right. Yes, well, yeah,
Two T's at the end.
two T's at the end. All right.
Yes,
Okay.
and no E. Yeah. I'll put it in the chat.
Okay. All right. Okay. It's good to see you can finally spell your own name. Yes. Okay. All right. Yeah, that's fine. Okay. All right.
Thank you, Dr. Sinclair.
Sure. Okay, doke. Have a good day.